The astronaut begins the journey far from the black hole, where space still feels calm and predictable. From this distance, the black hole cannot be seen directly, because black holes emit no light of their own. Their existence is revealed only through their gravitational influence on nearby stars and glowing clouds of gas. This black hole is classified as a supermassive black hole, similar to Sagittarius A star, the massive object located at the center of the Milky Way, with a mass millions of times greater than that of the Sun. As the spacecraft moves closer, the astronaut notices that the stars ahead appear stretched and distorted, forming strange arcs of light. This effect is known as gravitational lensing, a phenomenon predicted by Albert Einstein's theory of general relativity, where intense gravity bends the fabric of space-time and forces light to follow curved paths. Even at this distance, gravity is already shaping what the astronaut sees. Time aboard the spacecraft feels normal, but scientifically it is already changing. Strong gravity slows time itself, an effect called gravitational time dilation. To observers far away, the astronaut's clock would tick more slowly, while the astronaut feels no difference at all. This means that approaching a black hole is also a journey into the future of the outside universe. Soon, a bright ring of light appears ahead. This is the accretion disk, a swirling structure made of gas, dust, and torn apart stars. As matter falls toward the black hole, friction and extreme compression heat it to millions of degrees, causing it to glow intensely and emit powerful X-rays. This disk is often brighter than the combined light of all the stars in the surrounding galaxy. The black hole itself remains invisible at the center, hidden behind a boundary known as the event horizon. This boundary marks the point of no return. Once crossed, no signal, no particle, and no light can ever escape. The event horizon is not a physical surface, but a limit defined by space-time itself, where escape velocity exceeds the speed of light. As the spacecraft approaches this boundary, the universe outside begins to look increasingly strange. Light from behind the astronaut wraps around the black hole, creating a distorted, almost spherical view of space. This is caused by extreme space-time curvature, where directions lose their usual meaning. From the perspective of a distant observer, the astronaut would appear to slow down, freezing at the edge of the event horizon, fading into darkness. But from inside the spacecraft, the fall continues smoothly. This contradiction is one of the deepest mysteries in physics, showing how reality depends on the observer's frame of reference. And this is only the beginning of what the black hole has to reveal. As the astronaut crosses the event horizon, nothing dramatic seems to happen at first. There is no wall, no shock, no sudden darkness. This is one of the most surprising truths about black holes. According to general relativity, crossing the event horizon of a sufficiently massive black hole would feel completely ordinary in that exact moment. The danger is not at the horizon itself, but deeper within. Inside, gravity becomes increasingly uneven. The astronaut begins to experience tidal forces, a result of gravity pulling more strongly on the parts of the body closer to the black hole than those farther away. This process is known as spaghettification, where objects are stretched vertically and compressed horizontally. In smaller black holes, this would happen before reaching the event horizon, but in supermassive black holes, it occurs much later. Light behaves in unfamiliar ways. Photons trying to move outward lose energy and stretch into longer wavelengths, shifting toward red. This phenomenon is called gravitational redshift. Eventually, light becomes so stretched that it fades entirely, making communication with the outside universe impossible. At this point, the astronaut is causally disconnected from everything beyond the black hole. Time itself begins to collapse into a single direction. Inside the event horizon, space and time swap roles. Moving forward in time becomes as unavoidable as moving forward in space once was. The singularity ahead is not just a place, it is a moment in the future that cannot be avoided. The black hole's interior is governed by equations that science still struggles to fully understand. At the centre lies the singularity, a point where density becomes infinite and the known laws of physics break down. General relativity predicts its existence, but it cannot describe what truly happens there. Quantum mechanics, on the other hand, has not yet been successfully unified with gravity to explain this region. As the astronaut falls deeper, theoretical models suggest that all possible paths through space-time converge. Some hypotheses propose that the singularity may not be a point, but a region where space-time becomes highly distorted and chaotic. Others suggest that information may not be destroyed, leading to the famous black hole information paradox, a conflict between quantum theory and relativity. According to quantum physics, information cannot be erased, yet black holes seem to swallow information completely. This contradiction led Stephen Hawking to propose Hawking radiation, a process by which black holes slowly lose mass by emitting faint radiation at their edges. Over unimaginably long timescales, black holes may evaporate entirely, releasing their stored information in a highly scrambled form. From the astronaut's perspective, this evaporation is irrelevant. The fall toward the singularity happens in finite time. The closer the astronaut gets, the stronger the curvature of space-time becomes. Distances lose meaning, and the structure of reality becomes increasingly abstract. Some speculative theories suggest that the core of a black hole could connect to another region of space-time, forming what is known as a wormhole or Einstein-Rosen bridge. These solutions arise mathematically, but they are believed to be unstable and non-traversable. Still, they hint at the possibility that black holes may be gateways rather than endings. Other models propose that instead of a singularity, the black hole contains a Planck-scale core where quantum gravity prevents infinite collapse. In such scenarios, matter could rebound or transform, though no experimental evidence yet supports this idea. As the astronaut approaches the final boundary, all known measurements fail. Space becomes infinitely curved, time becomes undefined, and the equations that once described reality no longer apply. At this point, science can go no further, and the story reaches the edge of human knowledge. From the outside universe, the astronaut never truly crosses the event horizon. From inside, the journey ends inevitably. This duality reveals the true nature of black holes. They are not just objects in space, but mirrors reflecting the limits of understanding itself. The black hole does not merely destroy. It challenges physics, reshapes galaxies, anchors cosmic structures, and forces humanity to question the nature of reality, time, and existence. And somewhere beyond equations and imagination, the black hole remains silent, holding its secrets, waiting for the universe to learn how to ask the right questions. And so, the journey ends where science meets mystery. Black holes are not just cosmic monsters hiding in the dark. They are questions written into the structure of reality itself. They challenge our understanding of time, space, and existence, reminding us that the universe is far deeper and stranger than we ever imagined. The astronaut's impossible voyage was never about survival. It was about understanding, about pushing curiosity beyond fear and knowledge beyond comfort. Every black hole we study brings us closer to the limits of physics and closer to the truth hidden within the cosmos. If you enjoyed this journey into the unknown, support the continuation of this exploration by leaving a like on the video. And if you want more stories that turn complex science into clear, fascinating explanations, subscribe to the channel and become part of this growing universe of curiosity. Together, we will keep exploring the deepest mysteries of space, one story at a time by Universe Explained.